Periods and groups are two ways of categorizing elements in the periodic table. Periods are horizontal rows across the periodic table, while groups are vertical columns down the table. Atomic number increases as you move down a group or across a period, as well as that, as you move down a group or across a period, chemical properties of the element change. Now, let us introduce to you more about the periods and groups of the periodic table. The first thing that you may notice about the periods is the melting point patterns of the elements. As you go from left to right, the first thing that you may notice is that earlier elements tend to have a melting point as an upward trend, peaking somewhere in something like carbon, or in the transition metals case, vanadium and tungsten. But as you go more to the right of the periodic table, the melting points of elements begin to fall. Eventually, the melting point generally reaches the lowest once we reach group 0, aka the noble gases. After that, the next element will have a higher melting point, and the cycle goes on again. Elements generally get less metallic the more to the right you go. Now, let's talk about the groups from left to right. First off is group 1, which is the alkali metals, consisting of lithium, sodium, potassium, rubidium, cesium, and francium. These elements have some properties that are similar to other metals, for example, high electrical conductivity. But they also have some properties that differ from other metals. For example, alkali metals are generally softer and more reactive than the other metals, as well as having lower density. You will notice that as you go down the alkali metals, some of their properties will differ. For instance, lithium is a reactive metal with a relatively low melting point that readily reacts with water to form lithium hydroxide and hydrogen. Compared to lithium, sodium has a lower melting point and is more reactive, able to light the hydrogen gas that emits on contact with water on fire, allowing the hydrogen to burn with a golden yellow flame due to sodium ions. Potassium has a lower melting point than sodium and is even more reactive, reacting violently with water to form hydrogen that emits a brilliant lilac-colored flame due to potassium ions. Rubidium and cesium are in turn even more reactive than potassium, reacting explosively on contact with water. Due to relativistic effects, francium's reactivity with water is predicted to be less vigorous than cesium, but I'll explain more once I get to the francium video. Usually, alkali metals form ions with +1 oxidation state. Moving on to group 2, which is the alkaline earth metals, consisting of beryllium, magnesium, calcium, strontium, barium, and radium. Compared to alkali metals, alkaline earth metals are less reactive, harder, have a higher melting point, and have higher density. But they are still generally softer, more reactive, and have a lower melting point and density compared to most other metals. Alkaline earth metals generally form the +2 oxidation state. They acted halogens to form alkaline earth metal halides. All the alkaline earth metals except beryllium also react with water to form hydrogen gas and strongly alkaline hydroxides. The heavier alkaline earth metals react more vigorously than lighter ones. Compared to their neighbors in the periodic table, alkaline earth metals tend to have more stable isotopes, as they possess an even number of protons, and for any given even mass number, isobars with both an even number of protons and an even number of neutrons tend to be more stable due to nucleon pairing effects. Skipping over to group 17, we have the halogens, consisting of fluorine, chlorine, bromine, iodine, acetine, and tennessine. These elements are known for their darkening colors once we go down from fluorine to tennessine. Their melting points rise and their volatility decreases as we go down. The word halogen means salt former or salt maker, which makes perfect sense considering that halogens tend to react with a wide variety of metals to form salts. Notable examples include silver bromide, sodium chloride, which is also called table salt, and potassium iodide. These elements tend to form the -1 oxidation state. All of the halogens form acids when bonded to hydrogen. Elemental halogens are dangerous and can be toxic and should be handled with care. Moving on to group 18, which consists of noble gases, helium, neon, argon, krypton, xenon, radon, and oganesson. Under standard conditions, they are all odorless, colorless, monatomic gases, well, except oganesson, since there's a possibility that it is a solid with very low chemical reactivity, due to their outermost shell having 8 electrons, excluding helium, since that's 2. It is hard for these elements to lose or gain electrons, explaining why they are so inert. Now that the main groups are out of the way, let's move on to the lesser known groups. Starting off with group 16, consisting of oxygen, sulfur, selenium, tellurium, polonium, and livermorium. They are known as chalcogens, and they have some similar properties except oxygen and patterns. As you go down to chalcogens, they get more and more toxic. Oxygen, sulfur, and selenium are very important for the human body. Tellurium is used by some organisms, and polonium, especially polonium-210, is always harmful as a result of its radioactivity. All of the solid, stable chalcogens are soft and do not conduct heat well. Electronegativity decreases towards the chalcogens with higher atomic numbers. Density, melting, and boiling points, and atomic and ionic radii tend to increase towards the chalcogens with higher atomic numbers. Metallic properties also increase the lower you go. Moving on to group 15, we have nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. These elements are noted for their stability in compounds due to their tendency to form covalent double bond and triple bonds. However, this property leads to their potential toxicity, most evident in phosphorus, arsenic, and antimony, creating strong free radicals that accumulate and damage organs. While the chalcogens usually form the -2 oxidation state, group 15 elements, also known as pnictogens, usually form the -3 oxidation state. Next is group 14, also known as the carbon group. They consist of carbon, silicon, germanium, tin, lead, and fluorobium. The boiling points of the carbon group tend to get lower with the heavier elements, and the atomic radii of these elements tend to increase with an increasing atomic number. The densities also tend to increase the lower you go. For example, carbon has a density of 2.26 grams per cubic centimeter, while lead has a density of 11.3 grams per cubic centimeter. Moving on to group 13, we have boron, aluminium, or aluminum, where you live in, gallium, indium, thallium, and nihonium. Known as the boron group, these elements are notorious for violation of the octet rule by its members boron and aluminum. All members of the group are characterized as trivalent. Several group 13 elements have biological roles in the ecosystem. Boron is a trace element in humans and is essential for some plants. Aluminum has neither a biological role nor significant toxicity and is considered safe. Indium and gallium can stimulate metabolism, and thallium is highly toxic, interfering with the function of numerous vital enzymes, and has seen used as a pesticide. And finally, the transition metals, consisting of groups 3 to 12, and sometimes the lanthanides and actinides are included as well. They're metals, they are lustrous and have good electrical and thermal conductivity. Most are hard and strong, and have high melting boiling temperatures. The melting point generally peaks at around group 5 to 6, rising before and decreasing after, and they form many useful alloys and compounds of 2 or more different oxidation states, binding to a variety of ligands to form coordination complexes that are colored. Now that you know more about groups and periods, treat this as a warm-up, because our next video about elements is going to be the first element of the periodic table, hydrogen. Thanks for watching, and see you all next one.